Welcome to everybody. This lecture is to introduce you to the field of condensed matter physics. In fact, we give this lecture to the students, to the first grade students of the Moscow Institute for Physics and Technology, MIPT. But I believe that the average first grade student is approximately of the same knowledge as the advanced scholars. Therefore, with this presumption, I proceed. This is a plan of my lecture. After a short introduction, I will proceed with the introduction to the liquid. We consider, as an example, the simplest liquid we should know about all, like water. When symmetry and the order appears to be important, we consider broken symmetry, compressibility, fluctuations, short-range order in liquids, correlations, and the role of dimensionality. Finally, we will turn gears to the microscopic origin of intermolecular forces, and we will explain immediately thermal expansion, elasticity as a consequence of the van der Waals equation. Finally, if time left, I will introduce you to the quantum liquids, which are helium-4 and helium-3. Let's start with the history of development of civilization. The names of historical eras, like Stone Age, Bronze Age, Iron Age, are given in accord with the names of solid materials, the solid materials that determine the technological level and development of the society. Of course, you can correct me and say that on the cultural side, there are specific time periods, specific centuries which are associated, which are called like Silver Age or Golden Age, and are associated with enormous progress in poetry, arts, and so on. But we speak about physics, and let's proceed about in this way. From time to time, I will ask some questions, and since I don't see and don't hear audience, I will have no feedback, and therefore you have to repeat my questions, which I will present here. You have to address these questions to yourself to understand what was given in the lectures. Let us begin with the question. Assume that we know and fully understand all the fundamental laws of nature, and we have identified all the elementary particles. The question is, will we be able to explain all physical phenomena based on this knowledge? To illustrate the problem, I will show you a cartoon that represents a piece of copper. With a 1 cubic centimeter of copper contains 10 to the 23rd power atoms, 4 times larger electrons, and all of them interact with each other. If we indeed know all the equations, we can write them down, but just in advance, I will tell you that even for 3 interacting particles, there are only a small number of precisely solvable problems. And what should we do when we deal with the 10 to the 23 particles, like in 3D in 1 cubic centimeter of copper? The problem looks extremely complex and hopeless to solve. Even if the solution exists and we are lucky to solve these equations, we are unlikely to be happy with it and would be unable to use it, since it's impossible to overview 10 to the 23rd power variables. And how to proceed in this seemingly hopeless situation? It's well-known classical approach, which is called microscopic average variables. So we operate with the average density, magnetization, compressibility, etc. Parameters that characterize your macroscopic system. It's like an average temperature over the hospital. But in fact, we can see much more. We can take measurements of the fluctuations of these parameters and study their response to external field. The variables that characterize and distinguish various thermodynamically stable phases of matter and their microscopic properties. This is the way physics proceeds, and this is a classical way. As for the object of study, the condensed matter physics provide a framework for describing what happens to a large microscopic group of particles interacting with each other using known forces. What are these systems? And there are infinite number of any particle systems, from weakly interacting liquids to living cells, nanostructures, atomic clusters, quantum materials, superconductors, and up to quark-gluon plasma. A collection of atoms, as you know, can exist in different states. For example, helium exists as a gas in cylinders, as a liquid in dewars, as a solid crystal in low-temperature pressure cell, and at ultra-low temperature as a superfluid liquid without viscosity. The condensed matter physics studies these different states of matter. Clearly, the condensed matter studied fluids and solids. And fluids right now experience a renaissance associated with quantum fluids, spin glasses, superconductivity of liquid helium-3, and so on. Whereas solid-state physics is mostly important for technological development of the society and studies crystal, quasi-crystals, polycrystals, solid nanostructures, etc., etc. Both in their development on the physical side proceed along two major avenues. The left one studies the lattice parameters, molecular structures, interatomic bonds, elastic properties, etc. That's so-called atomic-like properties. And another avenue proceed with studying of properties of conduction electrons. So the next questions you have to ask yourself, what distinguishes a gas from a liquid? When I ask this question to scholars, they usually answer, okay, this is a density, and this is compressibility. This is right, but this is not a full answer, and the remaining part of the answer we will see in a few minutes. The question number 2 is, what differs solid state from a liquid? This is a little bit more interesting, a little bit more complex. We will study it, consider this in a few minutes. As an example, we consider H2O molecule. Although this molecule is not the simplest one, it doesn't have a spherical symmetry. We see it every day, from the morning when you wash your hand and from your hand and face, and you should know everything about it. Let's consider imaginary experiment. We boil the teapot and we see the steam from the teapot nozzle. This is a quite common observation. On the other hand, the air around us contains about 40%, has about 40% humidity, but we don't see the vapor. Why? Usually scholars answer that to see the scattered light, the wavelengths of the light should be comparable to the scattering, to the site of scatterers. This is correct. With this knowledge, we proceed further, and we think about clouds. As the temperature lowers, the average kinetic energy lowers, and we start seeing the vapor in the clouds, in the atmosphere around us. Then the next important question is as follows. The H2O molecules are neutral, and it's interesting to understand where the main intermolecular interaction comes from. Is this gravitational, nuclear, weak interaction, or electromagnetic? The scholars which I asked these questions, of course, after several minutes of thinking, they answer electromagnetic. That's correct. But let's consider this question in more detail. The answer is, correct answer is the dipole-dipole interaction associated with fluctuations. As a rule, this interaction is attractive. As a result, when potential energy of interaction exceeds kinetic energy of molecules, intermolecular interaction become important and start forcing molecules to join. But when we observe clouds and condensation of water vapor into the droplets, attraction leads to increased density fluctuation, cluster formation, lower energy, and lower entropy. There is slow dynamics emerge. Density on average continue to remain homogeneous, but only when averaging over large areas of space and large time intervals. Ultimately, this process attraction leads to the formation of another phase, liquid water, whose density is much greater. High density of one of the few fundamental differences between liquid and gas, the density. Let's place the water vapor in a vessel at a special density of 0.32 grams per centimeter cubic at room temperature. On the right-hand side, there is a phase diagram of water which you should know. We focus on the critical point first, which is shown by the blue arrow. As temperature decreases, we go from right to the left side. Density fluctuations grow and last longer. The system no longer looks homogeneous. There are areas with higher or lower density. When their size becomes comparable to the wavelengths of visible light, the scattering increases sharply, and the system begins to look milky foggy. This is the way we see in clouds. Thus, we actually observe the phenomenon of critical slowdown of fluctuations. In other words, this is divergence of characteristic lengths and time scales. This picture was due to a special choice of density to consider the critical point. In fact, if water is not at a critical density, say at lower density, which is depicted by a red dashed line, so we again decrease temperature, and we consider gas phase at some temperature below the critical one. Though the density is uniform, rare fluctuations to the formation of droplets of liquid phase occur continuously. As temperature decreases, the number and size of droplets increase, but none of them will grow large and last for a long time. Finally, when temperature decreases, again we go below the critical pressure. We cross the gas-liquid phase boundary, and the stable phase sharply changes. And this phenomena at the crossing the phase border between gas and liquid, this signify the first-order phase transition. Long before the size of the droplet starts diverging, some of them will grow to very large size, nucleating at dust or salt molecules. Above a certain threshold size, they no longer die out, but will grow over time and absorb other droplets and gas molecules. The size is determined by the growth kinetic. In other words, how quickly gas molecules can diffuse to the outer surface of droplet and join it. The growth of droplets during a discontinuous gas-liquid transition is faster than the growth of fluctuation at the critical point. This is one of the characteristic differences between a discontinuous or first-order phase transition and a continuous second-order phase transition, which we considered before. Divergent compressibility at the critical point. If you apply pressure to a gas, its density increases. In other words, the gas is compressible. In contrast, the liquids are believed to be incompressible. At the critical point, however, the liquid and gas phases with different density are in equilibrium. Pressure can cause a volume of gas to change into a denser liquid phase without expending energy. A small change in pressure leads to a large change in density. This is divergent compressibility. Now we have to consider this in more detail. I remind you Clapeyron and Clausius equation. Consider the two phases, vapor and liquid, in equilibrium at a given number of particles. In equilibrium means that a system has a minimum of the Gibbs free energy. Free energy is equal to potential energy U plus mechanic energy P times V minus thermodynamic part T times entropy S, temperature times entropy S. Since thermodynamic quantities are additive, for the two-phase mixture we have a sum of partial Gibbs energy, free Gibbs energy for the two-phase, and this is written below. We take variation of the free energy, equalize it, set it to 0, and then we immediately have an equation of minima V times dP equal to S times dt, where x1 and x2, of course, the amount of vapor and liquid respectively. For an initial amount of matter we get from this equation, we get what is written here and contained in a red frame. dP over dt equals to changes in the specific entropy over changes in specific volume. Upon evaporation water to steam or solidification water to ice, the heat is consumed. It is not released. Therefore, when we look at the boundary, again of the same phase boundary between liquid and gas, as pressure grows, according to Clapeyron and Clausius equation, the equilibrium temperature should decrease. dP over dt is positive, and this means that entropy, changes in entropy is of the right sign, and changes in the volume of the right sign. Close to the critical point, however, the symmetry of the liquid and gas phases is the same. As a result, one can bypass the critical point and go from the liquid to the gas phase, as it depicted by the orange line, without crossing the phase boundary. Now let's turn our attention to the left border between solid and liquid. This curve surprisingly has a negative slope. dP over dt is negative. Can this property be used for compression cooling of a water-ice mixture? It seems that we apply pressure and should go below in temperature, like in a refrigerator, but doesn't work, because the entropy of ice is less than the entropy of water, but the specific volume is greater than the water. You remember that ice is floating in the water. Therefore, dP over dt is negative, but the refrigerator effect will not work. Upon evaporation water to steam or solidification water to ice, the heat is consumed, so the heat variation is positive. If you choose some simpler molecules like argon, neon, hydrogen, then the slope of the solid-liquid boundary will be correct. dP over dt will be positive. Now let's talk about symmetry. And the question you have to ask yourself is, in which state is symmetry higher, in liquid or crystal? Usually when I ask this question to scholars, they say, okay, of course crystal, because the crystal has shiny facets and liquid does not. This is incorrect. The crystal is not isotropic and homogeneous like a liquid. The liquid is invariant with respect to any rotations and displacement, and the crystal is not. It is invariant only with respect to those translations, the rotations, which leave the periodic lattice unchanged. That's why a crystal has lower symmetry than a liquid. The liquid-solid phase transition breaks the continuous symmetry of the liquid state. Crystal is often called a phase with broken symmetry, continuous symmetry. Actually, a set of symmetry element translation or rotation that leave the liquid phase invariant forms a continuous group. In contrast, the crystal has broken continuous symmetry. Let's talk about long range and short range order. How to characterize the difference between a crystal and a liquid? Density is no longer a good distinguishing feature. The specific density of the liquid and solid is approximately the same. The average density of a crystal and liquid differ slightly, and the sign of distinction may be different. Crystal has a long range order that you, of course, know, and this long range associated with the periodically varying local density. How to distinguish experimentally the periodicity of arrangement of molecules in a crystal? As usual, you have to shine your crystal with the waves The waves can be either X-ray or electron waves. Either of them should have a wavelength comparable to the interatomic distance. As you shine your crystal with the waves, you consider the diffraction pattern, take a Fourier transform, and look at discrete peaks in the spectrum. This picture shows the reflection of the low-energy electron waves at the surface of a crystal. More precisely, by measuring the scattering of waves on a crystal, we identify the matrix elements K sample K prime between the incident and reflected waves, where K and K prime are the Fourier transform of the disturbance introduced by the sample on the wave vector. Anyhow, from the common wisdom arguments, you understand that the waves should experience diffraction on the periodic lattice. Discrete lines in the Fourier's reflection spectrum distinguish a crystal from a liquid. And this is a consequence of the long-range order. If you don't have an X-ray diffractometer or a low-energy electron diffraction at hand, then how to distinguish liquid and crystal? This is not a trivial question, because liquid can be similar to, at first sight, can be similar to a solid, like window glass. And then you have to recall shear rigidity. We will discuss this in a few minutes. How to distinguish single crystal and polycrystal? Then you have to recall dislocation pinning. When you're trying to deform single crystal, you can hear with your ears the sounds related with entrance of the dislocations into the single crystal. On the other hand, the polycrystal already has a lot of dislocations, and therefore its bending, its deformation will not be associated with the acoustic emission. So far I spoke about macroscopic averaged quantities. Now let's talk about fluctuations. Molecules in the crystal undergo thermal and quantum fluctuations. They don't stay at their place as pinned. Let's estimate the magnitude of thermal fluctuations first. The distortion of an elementary cell of the size A may be described by dimensionless values of deformation. X over A, X is a deformation of some parts. The force per unit area associated with such a deformation is G times X over A, where G is the elastic modulus, Young modulus, corresponding to a given type of deformation. The cartoon clarifying this, our imaginary experiment, is shown below, where two atoms are connected with each other with some springy force, and the spacing between them is equal to A. According to the Hooke's law, force per unit cell equals minus A squared, this is the area of our elementary cell, times Gx over A, which is equal to Kx, where K is the effective spring stiffness or rigidity. From the equipartition theorem, it follows that the average potential energy at a temperature T of an oscillator with stiffness coefficient K is given by the simplest equation, K times X average X squared average over 2 equal to Boltzmann constant times T over 2. Therefore, the mean square displacement X squared average equal to K Boltzmann T over K. And this is inversely proportional to the elastic modulus. G, if any of the elastic moduli tends to 0, then the root mean square displacement diverges. Thus, rigidity under shear deformation is a necessary condition for periodicity. This is the difference between liquid and solid, the rigidity under shear deformation. Now let's consider liquid versus solid. Microscopic difference. Consider if there is any order in a liquid. We learned that there is no long-range order. Let's think about short-range one. The liquid state differs from the gaseous state not in symmetry, but in density and compressibility. That's correct. That's so from the macroscopic side. Less obvious is the correlation of particles in a liquid, but in fact it's simple. The distance between particles is determined by the interplay of the repulsive and attractive terms of the interparticle interaction. For even though the density is uniform, the correlation between atomic positions are quite strong. The origin of correlation is transparent. If there is a particle at one point in a space, then another particle has no chance of being at the same point. Moreover, there is a good chance that the second particle will be approximately 1 diameter away from the first one. This is the reason of special correlation in the liquid phase. To be more precise, let's write down some simple equations. We consider first the regular single particle density. This is the first equation, and with upper indices 1, equal to average of particle density over the space. And this is given by a sum over all particles labeled with the index j of a delta function with the argument is difference between r, which continuously varies, minus rj, where rj is location of a particle. This is obvious a definition of a density. The two-particle density, which I wish to introduce, describes correlations in the density at points r and r prime between two particles. And by definition, the two-particle density equal to average of the sum over the product of two delta functions. For the first one is for the first selected particle, and the second one is for another particle. Let's introduce the pair distribution function, which is dimensional 1 and convenient to operate with. So we factorize the above equation, writing the single particle density for the first one, type particle, the second type particles, and the dimensional g as a function of coordinates of the two sorts of particles. For an isotropic matter like liquid or gas, the density on average is constant. Therefore, we can simplify this equation and write that the correlation function is equal to n squared times dimensionless g of r, where g is a radial distribution function because our system is spatially homogeneous. And this picture illustrates how the dimensionless distribution function changes with the distance. As we expected, there is a zero probability of staying of the second selected molecules close to the first one. You see that these two curves starts from point 8 for the liquid helium-4, or 0.9 for the neon argon, and then it rises to a lovely position and drops down to unlovely position. So the atoms in the liquid prefer to stay at a given distance, approximately 1.1 or 1.4 in this interval of interatomic distance, one a part of each other, and then there are some unlovely distance which they prefer do not stay at. These short-range correlations, they increase as you decrease the temperature, which is shown on the right-hand side. For water, these are quite well seen, that you can see two oscillations at least, and finally the correlation function tends to unity. And this again, the important difference between the liquid and the gas. In a gas, the correlation function does not experience any oscillations. It's constant, it equals to unity. So the density is suppressed near the center of the molecule, then increases sharply and further oscillates and quickly decreases to a uniform density. Let's switch to fluctuation in the space dimensionality. Water was an example of a three-dimensional object. Many materials, however, behave as if they are two-dimensional or one-dimensional systems. For example, the two-dimensional system, actually this is the layer of electrons which operates in all your silicon-based field effect transistors on your smartphones and computers. In one-dimensional systems, it is the background of organic crystals, of many organic crystals, or artificially made quantum wires. Theoretical models can be formulated in terms of arbitrary dimensionality. And often it happens that the dealing with the d equal to 2 is hard. Therefore, theorists introduce a continuous dimensionality as 2 plus, like 2 plus epsilon, or d equal to 4. And then at the end of the calculation, then they tend epsilon to 0. Now, fluctuations are important but not crucial in continuous transition in three-dimensional space. As the dimension decreases, however, the fluctuations becomes more and more increasingly important. It's easy to understand. In one-dimensional system, fluctuations destroy long-range order and phase transition completely. This happens due to connectivity. The only way one end of the 1D system knows what is going on the other end is by propagating information along the system. For an infinitely long 1D system, however, any fluctuation blocks the flow of information and therefore order. Since there are always fluctuations at a finite temperature, a one-dimensional system cannot be ordered except at t equal to 0. We conclude that the long-range ordered crystal phase cannot exist in one dimension. For 2D systems, there are many ways in which one end of the system is connected to the other. Fluctuations are strong enough to destroy long-range order in a system with broken continuous symmetry, but not necessarily strong enough to destroy phase transitions. Now we switch gears to characteristic length scales, energy, and potential. We know that characteristic atomic scale distance are from 1 to 3 angstroms, or 0.1 to 0.3 nanometers. This is the diameter of electron orbits, the size of atoms, and distance between atoms and solids. All of them are of the same order of magnitude. Now let's estimate what is the scale of electrostatic energy, Coulomb energy, at a distance of 1 angstrom. You put figures into these equations, E squared over A, and you obtain energy of 14 electron volts, or 160,000 Kelvin. At this point, you should think that if you take, say, differently charged atoms like sodium chloride, salt, which is used every day, their atoms are differently charged. It should, according to our estimation, melt at about this temperature, which is not the same, which is not, in fact, happens in practice. The melting temperature of salt is much lower. And this is because the Coulomb attraction energy is not the only parameter in the problem. To go to the other driving forces, we have to introduce a few just introductory information from quantum mechanics. Actually, the quantum mechanics is introduced at the second grade for students, but I will present only very simple arguments and very simple information which I believe you will understand. The quantum mechanics mean that particles are considered as waves. And for me, these two pieces of information will be important: the particle and waves, correspondence between particle and waves, and uncertainty relationship. The first one is enclosed into the red rectangle. For waves, we know the wave number, or wave vector, equal to 2 pi over wavelengths. And the energy is equal to h, Planck constant times frequency. Thus, you can associate wavelengths with the energy. For particles, usually, you know that energy is equal to m times v squared over 2. This is kinetic energy. If we introduce for particles a wave vector, which is equal to momentum over h bar, then energy can be rewritten as h squared over 2m times lambda squared. And in this way, we introduce a wavelength to a particle with a mass m and energy E. The uncertainty principle can be easily understood from the common wisdom, from the common sense arguments. Let's consider the wave in a space, any wave. It's written here, and. If you wish to accurately measure its period, then you have to take measurements over a long length. What, as I said, it can be written below in a red frame. It's a product of uncertainty in wave number or wave vector times uncertainty in the position, or uncertainty in a space position. And it can be set to any of these quantities can be set to 0. You cannot absolutely precisely, with that certainty equal to 0, measure both these quantities. Now, knowing these two important pieces of information of introductory quantum mechanics, we consider a wave of any kind wave which we put into a rectangular box. Let it will be the electron, which we know is a wave as well, and we enclose it, we confine it in a box with infinitely high potential barriers at, say, position 0 and A. If we confine box in a 1D box of a size A, then a standing wave is formed because there is zero probability of a wave to propagate outside the infinitely high potential energy barrier. Then the standing wave means that wavelength becomes equal to 2 times length of the box. Using our definition for the momentum, we rewrite this to the product P times air approximately equal to the Planck constant. With this knowledge, we rewrite the product delta K, delta X, approximately unity. We rewrite it to delta P, delta X, approximately H. We conclude that the quantum particle confined in a potential box cannot have a zero momentum. If it cannot have a zero momentum, then it cannot have a zero energy. And the energy can be estimated as usual way, p squared over 2m. Instead of p, we put delta p, and we estimate h over 2m a squared. And this is the energy of our particle, which is confined into a potential well. Note, importantly, there is no temperature in this equation. This is entirely quantum expression, and this is a zero-point oscillations which exist even at zero temperature. So the quantum particle cannot have a zero energy. Now, with this energy, we can understand why sodium chloride doesn't melt at 160,000 Kelvin. Because the kinetic energy of an electron or atoms confined to 1 angstrom box equals to approximately h bar squared over 2m a squared, approximately to 44,000 Kelvin. So these two energies, the one is Coulomb attracting energy and another one is the kinetic energy of confinement, are comparable, and they much greater than room temperature, which is 300 Kelvin. Therefore, if electron waves are spread out over a large distance and are not localized on the atomic scale, then we would gain in kinetic energy of more than 3 electron volt per electron. As a result, the intermolecular forces in condensed matter, in a solid, in a liquid, are determined by the interplay of the two effects. The first one is the Coulomb attraction between the oppositely charged particles or dipoles of fluctuating dipole moment, and lowering kinetic energy due to delocalization of the quantum wave functions. Of course, this is an idea solely. This is to give you an impression of how it is going on. Now, with this knowledge, we can consider van der Waals attraction. The problem of van der Waals expression can be easily solved in course of quantum mechanics, which is taught for the MIPT students at second or third grade. Here I will limit ourselves to finding just a qualitative answer solely. The atoms molecules, as a rule, are neutral, so their charge equals to 0. Therefore, the Coulomb attraction energy is 0. The dipole moment, often for symmetric molecules, is also 0. Therefore, dipole-dipole interaction energy, which would be p squared over r cubed, equal to 0. However, the dipole moments, the next approximation, fluctuate and induce fluctuation moment at the neighboring molecules. The resulting energy of dipole-dipole fluctuations is proportional to 1 over r to the 6th power. The physics behind is as follows. The atom induces dynamic polarization of the neighboring atom that results in the attraction. And this is illustrated in the cartoon. And the important result is that the energy of dipole-dipole fluctuating interaction is inversely proportional to distance to the 6th power. This expression is valid for any attraction between any pair of neutral atoms or molecules located at a large distance away. The attraction is called van der Waals force. It has a typical value of 10 MeV for atomic scale distances. Now, with this force, attracting force, the molecule should not collapse. There should be some repulsion to provide finite distance between atoms. The 1 over r to the 6th power attraction should be replaced by a repulsion at short distances. There must be an equilibrium state with a minimum energy value, otherwise the atom will collapse. This repulsion potential is modeled using the repulsion of hard spheres, for example. In quantum mechanics, however, repulsion at short distances arises as a result of the exchange integral between the electron shells overlap. For our simple consideration, it's, however, to choose any potential that varies with distance quicker than the dipole-dipole attraction. For example, hard sphere suggests potential energy equal to infinity when r less than r naught. It's a hard disk model, or potential energy rises like r to the 12th power, etc., etc. In practice, the Lennard-Jones so-called potential, or 612 potential, is most popular. It's written here, and it provides a minimum of the energy between two atoms. There is attractive part at long distances and repulsive part, as we discussed. This remarkable van der Waals interaction energy dependence on the internal atomic distance explains a lot. For example, it immediately explains us the origin of thermal expansion. Indeed, where the two wings of the potential be symmetric, there will be no thermal expansion. But in fact, the right-hand side, long range wing, is produced by a weak dipole-dipole fluctuating potential. And the repulsive part is much steeper. Therefore, as you increase energy, the amplitude of the vibrations, of atomic vibrations, increases, and the energy increases, and the mean location of atoms necessarily should increase. This explains the thermal expansion of solids and liquids. Looking at this curve, you understand that the elastic force rises as you stretching your sample, and it tries to compensate the applied stretching force. And this lasts until you reach the inflection point. Above this point, the elastic force doesn't grow. Physically, it means that you reach the elastic force limit. If you think about this picture a little bit more, you can even explain why the metals have much larger deformation limit than insulators. In metals, this van der Waals energy is also built with a contribution from electrons. And the electrons contribution is attached to the atomic positions. Therefore, as you stretch your sample, the electron part moves away, and therefore this inflection point moves in metals as well. Now, let's turn gears to the quantum liquids. Liquid noble gases consist of symmetrical atoms, and therefore the van der Waals forces are weak, while the atomic masses are low. Therefore, the atomic fluctuations are large, and the amplitude of their zero-point vibrations becomes comparable or exceed the interatomic distance. Indeed, the amplitude of vibrations is h bar over square root of m naught. Whereas the dimensional ratio of the amplitude of vibrations to the interatomic distance is h bar over a square root of m naught. The a interatomic distance, as we said, is about the same in all materials, in all liquids and solids. It's about 1 angstrom. If we put some figures, then we immediately find that the gamma equal to 0.6 for solid neon. But for solid helium, for solid helium-4 and solid helium-3, gamma is bigger than unity. It means that the amplitude of the zero-point vibrations, their quantum vibrations, is bigger than the interatomic distance. This is the reason why this matter is called quantum solids and quantum liquids. They have a great number of very interesting properties because of the large amplitude of vibrations, the large gamma value. Helium-3 doesn't solidify down to T equals 0, of course with no applied pressure. This picture shows the phase diagram for helium-3. As I said, this is a quantum liquid. The vapor to liquid border is about the same as for water, air, and any other liquid. But for solid, it's intriguing. There is no solid, as you see, down to T equals 0. To get solid from liquid, you have to apply at least 34 bar pressure. The next very intriguing feature is a negative slope of dP over dt. The negative slope for the liquid-solid phase diagram we saw also for water. But in case of water, that was a consequence of a quite obvious reason. The ice had specific density lower than the water. Here, the case is different. Here, the difference between density of liquid and solid helium is normal, of a normal sign. So the denominator is negative. And as contrast to water here, the difference in entropy is abnormal. The entropy of solid is bigger than the entropy of liquid. Solid is more disordered than liquid. And this is the only consequence of the quantum nature of liquid helium. The liquid is more ordered than solid. As a result of this dP/dt, temperature indeed decreases as you raise the pressure. And this is indeed can be realized in practice, and was for many years was one of the ways to achieve lower temperatures by so-called Pomeranchuk effect, by raising the pressure. And this is illustrated by a red arrow. Increasing the pressure, you go to lower and lower temperatures. Another feature which is entirely of quantum origin is the appearance of the superfluid phase in a system of helium-3, which are fermions, and are not expected to exhibit superconductivity and superfluidity. Here they condense at sub-millikelvin temperatures to a superfluid state. But this phenomenon is, of course, out of our consideration. And I wish to conclude with a take-home message. Now, condensed matter, material science, is a platform for technology and civilization development. It studies a wide class of matter, from biomolecules to black holes, and it is an intriguing field of research. It includes quantum physics and quantum chemistry of atoms and quantum physics of electrons. It incorporates many concepts like symmetry, topology, wave quantum physics, quantum invariance, composite quasi-particles. The latter merge quantum flux quanta with elementary charges and spin fractions. It uses mathematical apparatus of the quantum field theory, renormalization group theory, density functional theory, quantum Monte Carlo calculation techniques, etc., etc. Thank you for attention.